Okay, welcome everybody. My name's Paul Scheida. I'm the chair of biomedical engineering here at Columbia University. We actually have a very special event. It's actually multiple events. Today we have both our engineering tech CEO lecture, and that same lecture is also the Richard SKALAK Distinguished Lecture in Bioengineering. And today also is International Women's Day, and just so happens our distinguished lecturer is a woman CEO. So lots of things have met nicely for this day. But first, what I want to do is invite our dean, Shifu Chen, to come up and give a few remarks.
Thank you. Thank you, Paul. Really wonderful to join up here on this special day. As Paul mentioned, today we have a wonderful event to celebrate several things. Right? One is 2024 Richard SKALAK Distinguished Lecture in Department of Biomedical Engineering. And as all of you know, biomedical engineering is the youngest department in the school, but it's also one of the fastest growing departments in the whole school, in the university. So wonderful to have this distinguished lecture here today. And we also use this to celebrate a Tech CEO series. As you know, Tech CEO series in the school is for us to invite the tech leaders and thinkers come back to share their experience and their insights with our faculty and students and really inspire our thinking on how to use engineering and scientific expertise to solve a complex problem using expertise from different fields. So since we launched last year, we have heard from Binoy Bazin, the CEO of Saint-Gobain. Some of you probably were here. That's a company founded more than 350 years ago, even older than Columbia University. Columbia is 270. Engineering school is how many years? 160, almost 160. Kathy, you probably know. A test for our alum. Welcome back. And then last year in November, we heard from Columbia Engineering alum Rajesh Jain, a pioneer from India leading the .com revolution in the early few decades ago, and is a founder of a NetCore cloud. Today, as Paul mentioned, we continue the series with Catherine Corrigan, and she is the president and CEO of Exponent as our tech CEO speaker and also a distinguished lecturer today. Paul will say more about the SKALAK Distinguished Lecture Series. And Exponent, I just feel so excited about this, Catherine coming to give this talk, because I was looking at the information, learning more about Exponent. Exponent's mission focuses on multidisciplinary approach to solve the complex problem in the society. It's perfectly aligned with the school vision if you walk through the hallway of the building, Engineering for Humanity. Right. So both Exponent and Columbia Engineering committed using engineering scientific expertise solve the global problem challenge we are facing today. And her expertise, we'll learn more today, biomechanics, the impact in transportation industry, consumer products, just perfectly aligned with one of the key elements of Engineering for Humanity vision, that healthy humanity of our school vision. And she's leading more than 1,000, if I'm correct, engineering scientists in Exponent, and I heard has more than 50% of them has PhD and MD degree. That's a high bar, right? We have to really work hard, and I'm sure we have many actually alum working in the company already. And so her team really showed the best example how we can work across disciplinary with business, with policy, with law, social work, and public health in many fields to have an impact in the society. And as many of you know, this cross-disciplinary theme is a key signature of our effort here. Our undergraduate degree is uniquely known for cross-disciplinary education. In addition to engineering foundation, you will learn the core curriculum, right, in social science, in liberal arts, humanity, learn critical thinking, and really high-level strategic planning and how to apply engineering field expertise to solve a complex problem. And many initiatives we launched from engineering school across the school with 17 other partner schools on the campus also emphasize very much this cross-disciplinary theme that's shared by Exponent. For example, the AI initiative I'm co-leading with several colleagues The Data Science Institute, we have more than 300 faculty members. Several of our faculty members here are part of the Data Science Institute. The collaboration with Zuckerman Institute, My Brain Behavior, collaboration with Cancer Center on the campus here, as well as Uptown, and also collaboration with the business school and medical school in Biomechanics acceleration in translating technology into the marketplace. So it's really so exciting to see that vision share between engineering school and Exponent. So we cannot find a better speaker to really exemplify the vision. Looking forward to her lecture today. I'll turn over to Paul to introduce her. Thank you.
Thank you, Shifu. Just before I introduce our distinguished speaker, just want to give a little background on the Richard SKALAK Distinguished Lecture in Bioengineering. BME here has hosted this since 1996. For those of you that don't know, Richard SKALAK is a lifelong Columbia engineer. He got his bachelor's degree in civil engineering in 1943. Then, as many of you know, there was a war on, so he joined the Naval Reserve, actually was an instructor down in Virginia for sonar and radar operators. He came back to Columbia, became an instructor in civil engineering while he was getting his master's and his PhD. So he got a PhD in civil engineering and applied mechanics. And then I think a real inflection point in his career is when he looked at taking his expertise and his engineering acumen and trying to look at biological problems. And he became really a pioneer in biomechanics. And he's really credited with a whole bunch of groundbreaking work in looking at the mechanics of blood flow, of bone growth, and even the biological responses of implants. And so, you know, in addition to this lecture, he's recognized worldwide as a pioneer. In fact, the ASME, American Society for Mechanical Engineers, has honored him with an award, the Richard SKALAK Award, which is given to the best paper published in the Journal of Biomechanical Engineering. So a little history about that, and once again, he's a homegrown fellow from here at Columbia. Now, our distinguished lecturer, Shifu has already mentioned, is Dr. Catherine Corrigan, who's the president and chief executive officer at Exponent. She actually joined Exponent back in 1996. The same year that we actually started hosting this lecture. What a coincidence, right? She then was promoted to principal engineer in biomechanics, corporate vice president, and in 2012 was appointed vice president of Exponent's transportation group, where she oversaw a fairly large portfolio in the transportation group, overseeing vehicle engineering, biomechanics, human factors, data analysis, and so forth. And she was appointed president in 2016 and CEO in 2018. Her educational background, actually, we were joking, is opposite of mine. She actually got her undergraduate degree, her bachelor's degree at University of Pennsylvania in bioengineering. We were reminiscing about some of our old professors back then. And then a master's degree in mechanical engineering at MIT, and then a PhD in the Harvard-MIT HST program. And she is also an elected member of the National Academy of Engineering. So I'd like to invite Dr. Corrigan up to give her the come on up.
All right.
Give her this plaque. Present her with this plaque. Well, I'll do this too. Okay. And thank you very much, Catherine. And the lecture is yours.
All right. All right, thank you, Alexis. And thank you, Dean, and thank you, Paul, for that introduction. I was so excited when Ed Guo sent me an email a number of months ago. Ed Guo and I were actually lab mates together at the Orthopedic Biomechanics Laboratory at the Beth Israel Hospital in Boston, where we were doing our graduate work. But let's get into this. So when Ed called me, I didn't really know about the SKALAK lecture, and so I said, well, let me investigate and see what some of the past speakers were, and I saw some very incredibly distinguished academic researchers who have come and who have spoken with you and sort of shared their work, and I said to Ed, I'm not sure I fit that super well because I'm not a researcher in academia. But what I do, or what I did while I was consulting before I was running a public company, was to answer questions for clients that had real challenges about their products' performance in the field, questions about safety, questions about health, questions about the environment. And so I wanted to come here today and not necessarily talk about a decade or 2 or 3 decades worth of research that I've done, but rather how I have been able to harness the power of much research that has been done in human tolerance and injury biomechanics over many years and apply that to a real-world situation, a real-world analysis to help a client who needs to make some real decisions about their product. And so I'm going to give you that, but first, I want to tell you a little bit about Exponent. So Exponent is a multidisciplinary engineering and scientific consulting firm. You can see we have close to 1,000 consulting staff. Most of those folks have PhDs or doctorates in their chosen field. But the reason that we bring that kind of person to Exponent is because of their ability to solve an unstructured problem and to work on a multidisciplinary team. So to get those diverse perspectives working on that problem to come up with the best solution. We have offices all across North America, as well as in Europe and in Asia. We cover many, many different disciplines of science and engineering. And just to give you a feel for the breadth of the work that we do, it is across many different industries. It is across many different disciplines across the bottom there. So you can imagine all around the product life cycle, when clients have challenges with their products, stumbling blocks in their development cycle, disputes that arise in the context of litigation. They're contemplating needing to do a recall because of a safety issue. These are the kinds of problems that our clients come to us for, and we provide solutions. And so my background, I think Paul went through this, so I don't need to spend a lot of time on it. Paul and I did flip-flop almost to the year between Philadelphia and Boston, and a number of folks here that I was reminiscing with about their days at Penn. But I am a lifer at Exponent. I have worked for the same company my entire career. So I finished my PhD at MIT in 1996 and went straight to work in consulting. And so I didn't necessarily know exactly what I was getting into. I didn't have any clients or anything like that. But I knew that I wanted to be very applied and solve some real-world issues that were really of concern to clients. And my background from a research perspective was in orthopedic biomechanics. So I wrote my PhD related to bone fracture, very interested in trabecular bone, how things like bone density and bone material properties affect the failure properties of bone, looking at things like hip fracture risk and spine fracture risk. So very similar work to what Ed Guo was doing. I think he was working on fatigue at that time in bone. And so you all know what biomechanics is, right? Simply the application of the principles of mechanics to a living system, right? How does matter respond to force? But in biomechanics, that matter is biological tissue, right? It's linkages and loads. It's the same principles that we use in civil or mechanical engineering. And then what are those internal stresses and strains that bring about that response? That's really what biomechanics is. And there are some very simple examples that you can start to think about where biomechanics can really help to answer important questions. So, here we have a very simple static model of someone lifting a box, right? You can use simple principles of mechanics, static equilibrium, to calculate, and I don't have the number offhand, but you can calculate that compression force that's on that lumbar spine. And this is directly relevant to things like ergonomics, to injury to discs, for example, in the spine. And when you solve this simple equilibrium problem, what you learn is that the force on that spine, even from a simple lifting activity, can be multiples of our body weight. 300, 400, 500 pounds, depending on the mechanics of how you're lifting it, and so forth. And so this can start to inform decisions around medical devices that you might be implanting in the spine. This can inform decisions on how much weight restriction we should put on someone to avoid injury to the spine, right? So it's always about a balancing of risk, understanding the load that you're applying to the tissue, and then understanding the tissue's tolerance for that load. And of course, in a biological system, that can be very complicated because everyone's tissue is different, right? So we have to think about that as a continuum. So we study biomechanics at multiple levels, right? You can start at the cellular level. You can be looking under the microscope, applying microscopic strains to cells in vivo or in vitro to see how they respond chemically, right? You can move up to the tissue level. This is what I was doing my research in when I was a graduate student. Trabecular bone, it's that sort of spongy bone inside of our long bones, and you can try to understand what those properties are at the tissue level. We can look at the organ level, so the mechanics of injury to the brain, for example, functioning as an organ. How do we describe that? There's been a tremendous amount of research done in that particular area over many decades that we can use to apply to real-world incidents to really understand what's going on. You can look at it at the whole body level. This is one of the kinds of instruments, this anthropomorphic test device or crash test dummy that we use routinely at Exponent, and other researchers do as well, because you can't put a human into an injurious situation and study it, right? So you need a surrogate. You need something that is designed and has sensing systems and is designed to be biofidelic to mimic that human response at the whole body level. So this is just background for the kinds of levels that we can understand biomechanics. Now I want to move on to understanding injury, because that was really my area of interest. So what is an injury, right? Simply put, an injury is damage or harm caused by a physical trauma that's sustained by tissues of the body, right? So there can be lots of examples. Here we have an example of an abrasion, the picture. You start to get clues, though, when you see an injury, when you see it described in the medical records, and I'm going to do a case study to illustrate this. You start to get clues about what's going on there, right? So that abrasion, you can think about just hitting the tissue straight on and compressing the tissue. That might get you a bruise, but it's not going to shear the skin away, right? So you know right away that you've got something going on here that has to do with shear, or has to do with some kind of sliding motion between two surfaces, right? You can get these kind of clues. A bone fracture, another example, very close to my heart. This is one you can look at. This is a femur. I don't know if all of you recognize that. That's the long thigh bone going into that hip socket. But if you look at the femoral shaft, and I think I have a pointer here. Maybe not. Anyway, I'll just point to it. But you can see the spiral nature of that, right? It almost looks like a barber pole, right? Those old-fashioned barber poles. So again, you're getting some clues about the forces that must have been applied to that bone in order to create that kind of fracture pattern. It's got to be some kind of twisting, some kind of torsion, right? So we've got a piece of physical evidence that can help to elucidate what's going on. So the medical records become incredibly important in these individual cases where we're trying to understand the injury mechanics. You can have a ligament tear. This is just a graphic showing that's an anterior cruciate ligament. We hear about ACL injuries in athletes all the time. Well, there's only a certain type of force that's going to be able to create that injury, right? If you push, a ligament's like a rope. You can't hurt a rope by pushing on it, right? You have to have tension to do that. So again, you're getting clues about what's going on inside the joint by virtue of what's happening, what you're seeing in the medical records, what you're seeing in the imaging studies. An organ laceration. And so in this situation, we have, I found the pointer. There we go. So you can see these darker areas. So this is a cross-section. This is a CT scan. Imagine the patient laying on the table with their feet sticking out at you, okay? This is the spine. So the bright white is the bone. Right, where's Lauren? She knows a lot about that. She can tell me how well I thresholded this image. But if this big thing in here is the liver occupies a big space in your abdomen. These white things here, these are ribs, the cross sections of the ribs. But these darker areas represent, excuse me, actual laceration to the liver, actual tearing of the tissue in the liver. The mechanism for this is typically a very high strain rate compression of that chest and abdominal cavity, because the liver is a viscoelastic organ. And so the way you can get this literal fracturing of that tissue, it's kind of like silly putty. If you pull on silly putty super fast, it will fracture fairly brittly. But if you load it slowly, it'll just stretch and stretch and stretch and stretch, and it won't break. It's kind of like liver tissue and a lot of our soft organs, right? So again, you're getting clues based on the type of injury you've got. You can have tears within the vasculature that are related to blood flow. You can have shear in the wall. You can have, this here is an example of a spinal dislocation, a very dramatic injury, right in the mid-spine. You can see right here. And so, the list sort of goes on and on of examples, but all of these are physical evidence that can help us to reconstruct what happened in a particular injury event. So why do we study injury biomechanics? First of all, to figure out what happened, right? What's injured, how was it injured, and also what is not injured. This is a key thing when you're trying to reconstruct the motions and the forces that created a set of injuries. Knowing where the bumps and bruises are, knowing where they're not, is also important, right? Because you can use that information to rule out certain scenarios, right? But we also want to study injury biomechanics so that we can prevent injury in the future. So this has to do with the development and design of things like restraint systems, protective devices like helmets. You need to understand the mechanics of brain injury and concussion if you're going to design a football helmet to try to prevent that, in an NFL game or in a college football game, right? You need to study the mechanics of the skull to avoid skull fractures, and also therapeutic interventions. I know there are a number of folks who are studying various interventions around this, and understanding the mechanics of the tissue is critically important to that. So there's a reactive component, sort of a retrospective that's important, and there's a future-looking, safety-oriented objective here. So I want to give you a sense for some of the tools that we have to understand injury tolerance. This is a field that has been active since, it's been decades. People first started, they were literally dropping cadaver heads down elevator shafts to try to understand the mechanics of skull fracture and brain injury. So you can do injurious testing, right? This goes off. You can use cadaveric tissue. Animal studies are another way that we use to try to understand and correlate to what goes on with the human. We can use our crash test dummies, our ATDs, to understand that mechanical environment, right? We can also use real-world accident data. There are databases that are kept up by the government, so they are publicly available to various researchers, where accident data are stored. So they might have, and this is in the automotive environment in particular, so there will be things like in the database like the speeds of the vehicles and whether people were wearing their seatbelts or not, and the various injuries that occur. And so researchers like me can go into that database and try to understand some of the correlations and causal factors that can increase or decrease injury risk. So we use accident data. The tricky part about it is you can't control it. In a laboratory, you can decide exactly what those parameters are of that crash test, but in the real world, you got to take what you get. So it's a different kind of approach. But we can also look at non-injurious testing. And this is important because if I apply a force to someone and they don't get hurt, that tells me something about the tolerance. It tells me that we're below the tolerance for that injury, right? So what do we use there? Human volunteers. what are the acceleration levels on the head when somebody heads a soccer ball, right? We can measure that. You get a little bit of a crossover here between injurious and non-injurious when you start putting sensors in football helmets, because sometimes these guys do get injured and they do get concussed, and that data is telemetrically processed and can be used to try to really understand concussion risk. There have been huge advances in understanding concussion risk over the last 10 to 20 years once the technology became available to sense and transmit that data. So this is the universe of the kind of studies and tools that we have to understand human tolerance. And so how do you then kind of take that into a broader context of what is the injury risk? And here I like to show my sort of favorite family portrait. These are our ATDs. You have your 50th percentile male. You've got your 5th percentile female. You've got a 10-year-old. I think this is a 2-year-old maybe, and the 6-year-old, I think it is. But very sophisticated instruments with triaxial accelerometers in the head. There are axial load sensors in the femurs, the chest compression sensors and accelerometers. The neck is heavily instrumented. Over the years, researchers have studied and learned how to best correlate those sensor measurements with actual risk of injury to humans. And they've used these techniques, cadaver testing, animal testing, non-injurious testing, et cetera, to develop what those correlations look like. So we can take the dummy measurements, we can do that injury risk analysis, we can look at the Federal Motor Vehicle Safety Standard requirements. This is the kind of instrument that has to be used. If you want to sell your car in the United States, you have to prove that your injury metrics are going to be below what is likely to cause a certain degree of serious injury. So very important set of instruments. This is just one example. I'm not going to go into the details of the derivation, but decades of research leading to the development of what we call the head injury criterion. This is a resultant measurement that comes from the linear acceleration versus time curve that correlates directly to the severity of a brain injury that we see. And you can basically look at the acceleration versus time characteristic, and this metric takes into account not only the magnitude of the acceleration, but also the duration and the shape of that curve. So we get these very sophisticated metrics that we can use to predict, when the information comes out of the dummy, you say, well, that's nice, but the dummy didn't break. So is the human in that situation going to be injured or not? This is the kind of metric that we can use, and we can plot the risk of a serious injury. It's always a probability distribution because one human and the next human are not the same, right? So we have to look at it from the standpoint of risk, and we can plot that. So you can do that for brain injury, you can do that for neck injury, you can do that for femur fracture. All of these things have been developed over the course of time. So I think the best way to illustrate this in action is to do a case study and just show you the kinds of evidence that we're able to look at and how we're able to look at some of the clues that are available to figure out what the mechanism of an injury was and to answer some of the questions that arise in the context of that injury around the performance of a product and the safety systems associated with a product. So this is a rollover accident, and I'll get right into it. This is an actual case that I worked on as part of my work at Exponent. You can see the vehicle down here. It is not where it is supposed to be. So it was driving up here, and there was actually a collision at an intersection over here with another vehicle. But what happened is post-collision, this vehicle went over the guardrail, actually took out the guardrail, and rolled over down the hill. And as we get closer up, we can see the vehicle at the scene. Now you can see that there's a lot of extrication type of damage that's happened here, right? The doors have been cut away. You can see the seatbelt sort of hanging and various things. And you can also, we can identify where our injured occupant was sitting. So there was a woman sitting in the right front passenger seat. She was fully restrained in this accident, but she suffered some very, very serious injuries, which I'll go into. And so there are questions that arose in the context of this crash as to, the real issue was around the strength of the roof structure, and I'll get to why that matters. So this is a kind of mapping of the injuries that we use to understand from the medical records where the various injuries are and what the details are. So this is mostly really about the external evidence of injury. There was some bruising on the chest, you can see, and the arm. I talked about the seatbelt. There's a very specific pattern of bruising that arises in crashes when a person is wearing their seatbelt. This person had those signs, and there was physical evidence on the seatbelt demonstrating that it had been loaded in the crash. So very clear that this occupant was restrained. Some fractures, some injury to the left lower leg, some bruising to the flank, and there was a fracture of the sternum, some rib fractures as well. But the real serious injury was to the spine. This occupant had a very serious cervical spine injury, so that's the neck area. It was what we call a fracture subluxation, and I'm going to show you some of the radiological films so you'll be able to see what I'm talking about. But it was at the C6, C7 level, so if you reach back, that big bone on the back of your neck, that's the spinous process of C7. So that's right around where that injury occurred, at the base of the neck. And so there was the fracture subluxation there involving C6 and C7, complete tearing of the ligament that runs along the back of the spine. Now again, we're already starting to get clues. We have a ligament that's torn. You can't do that with compression. You're not doing that with twisting. That's tension. Right? So already we know that locally in the back of the spine in this area, we tore that ligament. Right? So we've got to be pulling on that somehow. We've got a crush fracture of the C7 vertebral body. Right? That means that there's compression. Right? So, what's going on here? I've got some tension back here in the ligaments. I've got a crush fracture. I've got compression here. I've got some compression here. I've got an end plate fracture of T3. So we're piecing together some of this, and I'll show you some of the imaging that helps us. So this is, again, another CT scan. Lauren, I filled this presentation with CT scans just for you. We can see the bones, right? So this is the base of the skull in the back. This is the front. This is the back. And so we work our way down. Here's our this is C2, this big one. Second vertebral body, 3, 4, 5, 6. And here you see the problem, right? So this is where the spinal cord runs, in this sort of dark area here. And this is not supposed to look like this. So this C7 has been compressed. It's almost wedge-shaped, right? So the front is compressed more than the back. And then the vertebrae above has actually slid forward relative to the one below. Okay, so we're getting more clues about what's going on here. So that's that fracture subluxation of C6 over C7. And the bilateral jumped facets, these are the joints in the back, and I think I have a better image, yes. These are the joints in the back of the spine. These are all nicely lined up. They're almost like a sawtooth, they're diagonally opposed to one another, but when you get to here, this one is supposed to be back here. Like this is all supposed to be straight, but it has jumped over the one below it, right? So we have another clue to what's going on here. And then we can look further down the spine at T2. So this is the second thoracic vertebral body, right? This is C7, T1, T2. This has seen some compression too. This is compressed, not as much as this one in the front, but we know we've got evidence of axial compression along the spine. It's the only way you can do that and create that kind of fragmentation. And another thing to note here is this is a fracture at C7, which is comminuted. So it means that there are fragments. It means there is a higher energy associated with this fracture than sort of a non-comminuted fracture, right? So you're getting clues about speed and energy that are being applied. We can look at this from the front. You can see that comminuted crush fracture, again, of C7. You see some of those fragments, and so on. And so what I want to do is get into, now that I've illustrated the injury, we've got to figure out, well, how did this happen in this crash? We need to understand the mechanics of what the vehicle was doing, and we need to then correlate that with, well, what is the occupant going to be doing in response to those vehicle motions, right? So this is an actual dolly rollover crash test that was performed at Exponent's Test and Engineering Center in Phoenix. And I'm going to click the video in a second, but let me just give you a little context. This is not intended to be a recreation of the accident that I'm describing. This is more of a research type test to illustrate what the mechanics of rollovers look like and how the occupants inside move. So what you're going to see, there's going to be a dolly with a vehicle on it that's going to come into the field of view. We're going to get that dolly up to a very specified speed. We're going to stop it, and the vehicle is going to keep going. So you're going to see a series of airborne phases where the vehicle is in the air and it's rotating, and then it's going to hit the ground. And it's going to be rotating in the air again, and it's going to hit the ground. So it's a series of airborne phases interspersed with vehicle-to-ground contacts. And it's when those vehicle-to-ground contacts occur that the injury risk happens. So let me play this. We've got the audio on for drama. So you can see there that series of airborne phases with the vehicle rotating. Some of the rotation rates can be very dramatic in these high-speed rollovers, a full revolution per second, sometimes even up to 2 revolutions per second. You can see what some of the drop heights are for those vehicle-to-ground impacts that can create the potential for injury. So what's going on inside the car? I am going to show you some of the video of the occupants in a minute, but I want to first give you an illustration to just explain the basic physics, and it's not hard. If any of you have ridden on an amusement park ride, you know, the ones where it just kind of rotates around and you stick to the wall and the floor drops out from under you, it's just centrifugal force, right? It's just basic object in motion wants to stay at, object at rest wants to stay at rest, and the thing is turning around me, and I'm going to tend to go away from the center of gravity. That's what happens in the airborne phase of a rollover. So we've got occupants, in our case, we're looking at that right front passenger, and she's in her seatbelt, but there are forces that want to pin her up against the side of the vehicle. She's moving away from the center of gravity of that vehicle because it is rapidly rotating in its airborne phase. So what then happens when you come from your airborne phase into a vehicle-to-ground contact? And in this particular instance, we had evidence on the outside of the vehicle that it had a significant vehicle-to-ground contact to the roof directly over the head of that right front passenger. And so the kind of kinematics that are going to occur to this occupant, if you imagine a ground plane here, her head is essentially up against the roof, and I'll show you that in a moment because of the centrifugal forces. That part of the roof is coming into contact with the ground. The kind of injury that we see is actually very similar to the kind of injury that happens in diving, when someone dives into a shallow pool. The head stops, the body keeps going, and the neck is not designed to withstand that kind of force. And that's what happened in this particular instance. So we took some of the evidence from the vehicle reconstruction. This is part of that multidisciplinary approach, right? We have to work with those vehicle engineers. They're looking at the scratch patterns. They're looking at the deformation of the vehicle. They are reconstructing those vehicle motions. And then they hand it off to the biomechanical engineer to understand what's going on with the folks inside. And so one of the things we needed to do in this case was to investigate, just in a static environment, what kind of excursion a restrained occupant would have within the seatbelt when the vehicle is inverted. That was important to understanding the risk for this kind of neck injury given a vehicle-to-ground contact. So this work was done at our Test and Engineering Center in Phoenix. And what we do is we get a surrogate who is of similar height and weight to the occupant that was in the vehicle. We'll put her in there. The seat is positioned in the same way. We put her in that seat belt. We lock that seat belt. And then we put her on a roll spit. And we turn the vehicle upside down. It's kind of like a barbecue. It goes very slow. And so, there she is. She's in the right front passenger seat, and we can zoom in. And so we've got our tape measures on the seat belt so we can correlate with the physical evidence that we saw in the crash on the vehicle. But we can see, she's hanging away from the seat. There's nothing wrong with this seatbelt. Seatbelts have play. You can move in your seatbelt. If you had to wear a seatbelt that wouldn't allow you to move, you would never wear it, right? So, and it has to prevent injury not only in a rollover, but in a frontal accident and in a rear end accident and in a side impact, right? So it's designed very intentionally to have some excursion within it. And we can get up nice and close and see she's within about 1/4 of an inch of the roof, just under static conditions. So we're not rotating at a revolution per second here. We're just hanging upside down. And this is what we see. And so we can look at that from different angles. We only keep them upside down for about a minute. It's very quick. But we're getting some more insights into what was going on inside this vehicle in order to produce this injury. And here what I've done is just kind of juxtapose the kinematic illustration with what we saw in the CT scans. And if you imagine, that diving type of mechanism, the head stopping, the body, the torso, when the head is coming to a stop, the torso wants to keep going, right? And that's going to place a significant axial load on the spine. And what happens to the spine under those circumstances is it tends to buckle, because it's like a slender column, it's segmented. And so there's actually been a whole lot of work done at Duke University and other places over the years to characterize the mechanics of cervical spine injury under these types of conditions, diving accident type of conditions. And they have been able to show this sort of, going from a normal, which is the dotted line, to when you apply a rapid load, you create this almost S-shaped buckling pattern. And you can see, you're getting extension in the upper part of the spine because, again, your person is upside down. But you're creating flexion. You're creating a forward curvature, almost a chin-to-chest type of curvature in this part of the spine. Now, remember, we had injury that involved compression of C6 and C7, but we also had that ligament tear on the back, right? Well, that's very consistent with a scenario where that base of the spine is being bent forward. So at the same time we have compression, we have this buckling phenomenon that's creating localized flexion and tearing that ligament. And there's some really groundbreaking research done over many years, again, at Duke University, to really understand the loading conditions. People had tried for decades to reproduce this injury in the laboratory, and they failed because they were trying to just take the chin to the chest and just flex the spine, and they couldn't create the injury because the chin would run into the sternum every time. You couldn't get the amount of flexion that you needed locally by just shoving the chin into the chest. But what these researchers found at Duke is that you could constrain the rotation of the head, and then you would be able to get localized flexion. You can see the widening of those spinous processes. That ligament runs in between those spinous processes. That's where the ligament was torn. So what we have here is a combination of compression that crushes the bone, and we have flexion that locally tears the ligament and allows those vertebrae to slide relative to one another. This is another little video, again, courtesy of the folks at Duke University, that shows this. And this is an actual recreation taken from a specimen. They used markers, they tracked them during the experiment, and you can see this buckling phenomenon that creates this bilateral facet dislocation. We're applying the load, and then you can see how they slide relative to one another, right? And that was the mechanism that we really were dealing with here. So Coming back to some of the vehicle testing that's relevant here, I want to take you inside the car, the one that I showed you a little while ago, that dolly rollover test. And this was a series of tests that were published by folks at Exponent a number of years ago. It utilizes a Subaru Forester, which actually is a very high roof strength vehicle. It has at the time, it had one of the highest roof strength to weight ratios available in the fleet. All kinds of sensors and the ability to track the motion of the roof. You can see we have crash-worthy cameras. They're high-speed film, so tons of instrumentation on our dummies. We're measuring the neck forces. We're getting head accelerations. Lots and lots of data coming off of this, including the high-speed video. And I can show you some of that onboard video right here. And we're going to see those kinematics of sort of being up and away from the center of gravity during the airborne phase. And then you can see some of those vehicle-to-ground contacts, like right there. The head is up against the roof is hitting the ground. What's going on there? We're measuring what's going on at the neck. We're looking at the timing of the injury and the mechanics relative to the movement of the roof to try to understand, if ultimately the question was, if you had a stronger roof, would it have made a difference? That was really the fundamental question that we had here to try to answer. I'm going to stay over here just in case I have any more video. So one thing we can do is go frame by frame and look at that video versus the data that we're acquiring. So on the left here, we have B-pillar displacement, which reflects the roof deformation. And here we have the force on the neck as a function of time for that dummy. And we can step through it. So we've already gotten the neck force down. This is in newtons, so we're between 6,000 and 7,000 newtons of compression being applied to that neck. And we've got less than an inch of vertical displacement of the roof. So very little, and yet we've still maxed out our neck force, right? So because of the way the timing is working in this kind of kinematic when the occupant is already against the roof, there's a compression force applied to the neck that happens even more quickly than the crush happens to the vehicle. And so the next thing we did was, well, let's create a vehicle with a super strong roof and do a drop test and see if it makes a difference. And so that's what we did. We positioned our crash test dummy in the right front passenger seat, very similar to our human surrogate that I showed you a little while ago. Lined up the head at the same location that we learned of, being conservative, that it was only the static excursion. Dynamically in the crash, this occupant would have been pressed against the roof before the roof-to-ground contact. And then we do a very controlled inverted drop test to simulate that vehicle-to-ground contact. And this vehicle has a specific pitch angle, a specific roll angle, a specific height from the ground, and the timing of the release has to be very precise in order to get that drop to be just right. And we can show that here.
3, 2, 1, fire.
So you can see that sort of diving kinematic where the head stops and that torso keeps going. And we can, again, track that frame by frame and look at our roof displacement, which is in the sort of orange. And we can look at the neck loads. So you can see those neck loads in white and in blue are peaking, right around about an inch, a little more than an inch. The one thing I neglected to note about this vehicle, we put a roll cage in the vehicle. Like in auto racing, big metallic tubes that literally you can roll and roll and roll in auto racing and you won't see any damage to the roof other than scratches. We basically recreated that and made it almost infinitely stiff to see if that would make a difference, if you could, in theory, build your vehicle that way. And when we go back and we look at the magnitude of that loading of the neck, this red dotted line that I've indicated here is what is considered the threshold for creating serious injury based on those injury risk curves I talked about a little while ago. And so you can see in this particular kind of crash, there is a risk of exceeding that injury assessment reference value, that IARV that we call that. And so there, even in given the severity of this crash, even in a scenario with a very stiff, very strong roof, we still have a risk of serious injury in that instance. So that's a case study. I also wanted, if I have a couple minutes, so I'll just do these last few slides, because I also wanted to share a little bit of the actual research work that we're doing at Exponent as well in biomechanics. So we do a lot of work that's very applied, case-specific analysis, but when we see gaps in the tolerance literature, we will look to try to fill those and answer those questions. So one of those gaps that we noted was looking at injury tolerance of spines with a certain type of pre-existing degenerative condition. You know, many of you who do orthopedic work, what do? You look for the best specimens you can. You exclude the ones that have lots of degenerative changes, right? Because it's hard to control for that. So there's this gap in the data. We see in the real world, lots and lots of people have spines that have degenerative conditions. And there are this family of conditions, including what is called DISH, diffuse idiopathic skeletal hyperostosis. But what it is like the spine, the vertebrae kind of fuse together, right? So normally you have a lot of flexion with your discs in each of these functional spinal units. But if you have a lot of overgrowth of that bone, it becomes very, very stiff. And these are occupants that are in crashes just as much as the ones with the healthy spines. And so we saw an opportunity to do some research to understand, well, what are the differences in tolerance between a healthy spine and a spine with this kind of pathological condition? And this is really hot off the presses. This is work we did, I think, around December and January. So still, to be published and all of that. But the application, what we were seeing in the field, was during rear-end impacts. If you imagine someone in an automotive seat, they get hit from behind. The biggest part of the restraint, it's the seat that they're in. It's the seat that is pushing them forward, right? But we were seeing fractures of the thoracic spine that were due to extension. So like a bending backwards of the spine. And so, or a shearing, as we see in this particular example. You can imagine that impact acceleration happening, the occupants interacting with the seat, and we're seeing these kinds of shearing. But we're also seeing it in the context of, these very significant degenerative changes. So our team decided to go out and do a study on this, and they were able to obtain paired specimens. So with the DISH phenomenon, without the DISH phenomenon. They set them up in the laboratory. I don't have time to go into all the details, but we have a biomedical laboratory in our Philadelphia office. And they looked at these 4 vertebrae segments to understand the stiffness, the flexion and extension range of motion and all of that, the loading tolerance. And so what they found, and these are some image reconstructions of the specimens. Here's a normal one, right? Looks pretty good. You've got actual disc spaces here. This one, you have bridging areas of bone. So you can imagine that's like a much stiffer unit. It's not going to be able to really absorb as much energy because we hypothesized that there would be a much smaller range of motion. And that is, in fact, what we found in some of these preliminary tests, that there's a much lower level of torque that can be sustained by these spinal units, and also a much lower level of energy in those spinal units. So, we like to find opportunities to contribute to that basic science research to help folks who are working on, applications and have gaps to fill in those various areas. And so that is all I have, but I am happy to answer questions, and I think I landed on the right slide as instructed.
I can start. We have a virtual question.
Yeah, great.
From Pavlos Silvestros. He says, fantastic presentation of how to apply biomechanics in the real world. You talked about how theory and experimental methods are used to solve your question, but how are computational models such as multi-body or FE models used to help in these applied questions, such as your presented case study? And if they're not commonly used, what is the main reason for not using such models? Thank you.
Thank you for that question. So we absolutely use simulation tools as part of our analyses. It's not in every case. Back when I was doing this kind of work a number of years ago, we didn't have as much computational power. The expense associated with running those kinds of models tended to be even more, frankly, than the expense of actually running a test. And so we often would lean toward the testing environment. But as computational power has increased, as the sophistication of the tools has increased, there's more and more of an opportunity to use dynamics models, multi-segment models. MATIMO is one of them. I can't remember what MATIMO stands for, but it also incorporates finite element models of tissue. So depending on how sophisticated you want to get, there is absolutely a role for modeling in case studies, and I think we are seeing it more and more, but certainly not in every case.
Great. Thank you so much for this wonderful talk. I'm just curious, doing science is so expensive. What you showed is fantastic. So in academic setting, we got government grants to do science. So in industry, how you get funding to do this expensive research?
Yeah, you're right. It isn't cheap. And we have a very simple business model. At our firm, like most high-end professional services firms, we bill by the hour. And so, probably 85% of the work that Exponent does is the cost is each person has a rate per hour depending on their credentials, their experience, the market that they're in, et cetera. And we will build up a budget for things like these tests or things like our analyses in order to meet that. So, this is what clients are always concerned about cost, but they also have a lot at stake. And they usually call us when, are they facing a potential recall? That's a hugely important decision. And so, they may not be happy about having to spend those dollars, but they see the value because of the importance of the decision that they need to make. Even if it's a dispute, they need to understand, should I resolve this? Or should I go all the way and risk, a verdict in a jury trial? They need to make a really good decision, and we need to tell it like it is to them. So we charge for that. One of these, that drop test, with including, we have to buy the vehicle, right? That's a piece of it, but that might have been a $50,000 test. For that few seconds, you got to get it right the first time when you're doing something like that, that's for sure. Yes? Oh, let's wait for the mic so we can get our folks online to hear.
So your conclusion was the deflection of the roof didn't contribute to the severity of the injuries or didn't contribute much to it?
That's exactly right. By putting a roof that was just about infinitely strong and running through the same kinematics, we saw loading levels that are consistent with the pattern of injury as well as the severity of that injury. I've seen other instances in rollovers, though, where a lot of that conclusion has to do with the fact that the occupant was against the roof at the time of the vehicle-to-ground contact. But if you're in a situation where that's not the case, it can be very different, and you might actually avoid the injury if you don't have the deformation. So it's not a universal conclusion, but in this particular case, that was the conclusion. I think we have one in the back there.
So I know you have locations all over the country. How do you as the CEO think about segmenting or not segmenting certain initiatives based on geography? Yeah,
it's interesting because when I joined Exponent many years ago, we were fundamentally organized by geography. So it was this office, and that had a leader of that office, and this office, and you can imagine the silos that were created that way. And so actually my predecessor as CEO, Paul Johnston, back about 20 years ago, he reorganized the company into national disciplines. So we organize ourselves in that way, independent of geography. And that was really transformative for the business and really allowing us to grow and really encouraging that multidisciplinary collaboration, because you want to connect the whole ecosystem. That's one of the secret sauces to Exponent, is you can tap into that network and you can get that multidisciplinary team that's independent of geography. And with virtual tools now, we do an even better job of collaborating across the borders. So there's a lot of benefit to the local environment too. There's local business. Every office has its own culture and the things that it specializes in. But we've worked really hard to build an integrated business. We have one down here.
Thank you, Dr. Corrigan, for the lecture. It certainly aligns with the motto of Columbia Engineering, that is engineering for humanity. As you mentioned, you provide solutions, end-to-end solutions. So I would like to get some more info on that solution you provided to this problem.
Yeah, so the context of this particular case was product liability litigation, right? So there was a lawsuit that was filed against the manufacturer of the vehicle. And the question that was, the allegation that was made is that the vehicle was defective because it didn't have a strong enough roof. And if it had been designed better with a stronger roof, that the person would not have been injured and would have walked away in the crash, right? So it's an important question in the context of our justice system to apply rigorous science and get the right answer. So that's the context to which that question was asked, was in a particular lawsuit.
Thank you. Thank you.
Yes.
Proceeding along the same lines,
Yeah.
Apart from the lawsuit in question, what would you suggest as the solution to the problem, irrespective of that?
Yeah. One of the best things that has probably happened in terms of automotive safety technology to prevent this kind of injury is electronic stability control. That's the kind of technology that prevents you from rolling over in the first place. So not that there isn't work that has also been done to, improve restraint systems and customize those restraint systems for different sizes of individuals and, look at different materials for those restraint systems and looking at the seats that are sat in. I haven't been personally involved in the forward-looking part of that, but I know that folks within those automotive OEMs are always looking at injury tolerance and kind of that next set of technologies that's being used. This particular accident is probably a 99th percentile accident in terms of severity. It's very rare. So you might be able to design a system that would prevent this injury and this crash, but you then might have created an issue for an occupant who's in a frontal crash, which is something that happens much, much more frequently, right? So these design trade-offs are things that our clients are thinking about all the time, and they do, tap into us for certain pieces of that as well. Got a couple in the pink shirt here.
Hi, thank you for your presentation. I'm curious to know, how do you determine which type of experiment is the optimal one? So I see you can do it in the lab, you can also do live demos. How do you determine?
Yeah, it's very much it's an experience-based assessment. It's a case-by-case assessment, and that's part of the value when you think about being a consultant. It's part of the value that you bring to your client, because they come to you and they didn't come to us and say, I want you to run this drop test, right? They came to us and said, there's this allegation, how do we figure this out, right? So part of the value we have is figuring out how to figure it out. And so at Exponent, we really pride ourselves on coming up with novel test methodologies that aren't standard to be able to answer these questions. So there's a whole lot of experience. I mean, Exponent has been in business for over 50 years, but we have people who are sitting on standards committees for various industries. We have people who are very involved in the scientific community, so keeping up on what the latest methodologies are in the context of those incidents. So it's part of that secret sauce that we bring to the equation. It's not easy.
We have a follow-up virtual question real quick.
Great.
So he says, if I could follow up, currently during your consultancies, is more confidence placed on results from theory and experimentation compared to simulation results? I ask because, for example, the FDA and EMA are starting to accept evidence from models and simulations more and more with new standards such as ASME V&V 40.
Yes, so in certain areas there is absolutely a trend toward using models. One of these particular areas is around chemical regulation and pesticides. So there is movement toward wanting to do less animal studies and more sort of in vitro and modeling techniques. And so there is a trend toward that. The challenge with simulation is, we've all heard garbage in, garbage out, or how Kathy likes to say it, good data in, good data out, right? And so a simulation is something that can be, I mean, I've seen some pretty awful simulations in my day in sort of the legal context. And so, you know, you have to make sure that you've got something that is peer-reviewed, that the inputs make sense, and that you can back up all of those inputs. So, you know, I as a consultant always loved when I could just set up the test and let the laws of physics demonstrate what's going to happen. Then there's no question, right? And in that kind of environment, you know, being able to demonstrate that can be very important. But he's right, in the regulatory environment, especially around chemicals, there is absolutely a move toward doing more modeling, and it is more accepted at those regulators.
Okay, I think we want to really thank Dr. Corrigan for a fantastic talk. Also, I'd like to invite Dean Chang up to just say a few closing remarks.
Well, thank you, Catherine, for the fascinating talk. As you can see from the question, student faculty really very inspired by this aspect. And as a reference point, a lot of our students after they graduate actually right now, not only continuing for graduate study or maybe starting company, are considering consulting firm as possible career path. So your experience on pointing out the novelty and innovation in this case by case study, really very insightful. So we will have Catherine here today for more meeting, and really thank you for her for this wonderful talk. Thank you so much.
Thank you. Thank you.